In this episode, let us discuss about parallel axis theorem. Parallel axis theorem is a transfer theorem. That is, it is used to transfer moment of inertia from one axis to another parallel axis. So we use parallel axis theorem to find moment of inertia of plane laminas or plane areas. So in that case, it is used to transfer moment of inertia from one axis to another parallel axis. That is, suppose we have a plane lamina of area A. Let us consider an axis XX that is lying in the plane of the area, on the plane of the paper. Now, let G be the centroid of the area A. That is, the centroid of the whole area lies on this axis, XX axis. So, this axis can be called as a centroidal axis. Now, again suppose that we know the moment of inertia of this plane lamina about the centroidal axis. We know its numerical value. Let the numerical value be Ig. Now, let us consider another axis AB which is parallel to the centroidal axis. Now, we have to find the moment of inertia of this plane lamina about this axis AB. Let that value be IAB. So, this parallel axis theorem will give a mathematical relationship between Ig and IAB. That is, between the moment of inertia of a plane lamina about its own centroidal axis and moment of inertia of the plane lamina about another axis which is parallel to the centroidal axis. So that is why it is called as a transfer theorem. To use this parallel axis theorem in a problem needs to satisfy two conditions. They are, first one is, the two axes should be parallel to each other. That is the first condition. So as we have seen in this figure, axis XX, that is the centroidal axis, and axis AB, both of them were parallel to each other. So that is the first condition. Then second condition, one of the axes must be a centroidal axis. That is, here XX is a centroidal axis and AB is a non-centroidal axis. So one of the two axes that we consider must be a centroidal axis and both of the axes need to be parallel to each other. So let me ask you something. I have another axis CD. This axis CD is parallel to XX axis as well as AB axis. Can we apply parallel axis theorem between axis AB and CD? No. Why? Even though the axes AB and CD are parallel to each other, neither of them is a centroidal axis. So we cannot directly apply parallel axis theorem between AB and CD. But we can apply parallel axis theorem between axis AB and XX, as well as between axis CD and XX. Now let us derive the theorem. Let us consider a plane lamina of area A. I will write the values here of area A. Let G be the centroid of the lamina and let this axis pass through the centroid of the lamina. So this is an axis that lies in the plane of the paper or in the plane of the lamina, and this axis passes through the centroid of the lamina. So this is a centroidal axis. Let us consider another axis AB such that this axis is parallel to the centroidal axis GG and is at a distance h from the centroidal axis. So h is the distance between the two parallel axes. Now let us consider an elemental area dA. An elemental area dA whose centroid is at a distance y from the centroidal axis of the entire laminate. So this is an elemental area dA. It is at a distance y from the centroidal axis. Since it is a very small area, we can say that the distance from the centroidal axis to the centroid of the area, or distance from the centroidal axis to the elemental area, both can be taken as same because this area is very small. Now let us take the first moment of elemental area dA about the axis AB. So first moment of elemental area dA about axis AB. What will be the value? How will we take moment? You have to multiply the area with the perpendicular distance from the area to the reference axis. So here the reference axis is axis AB. So the perpendicular distance from the reference axis to elemental area dA is h plus y. So that multiplied by dA will give the first moment. Now second moment of the elemental area dA about AB. How will we take second moment? You have to multiply this moment value, first moment value, again with the perpendicular distance. dA into h plus y into h plus y. That is dA into h plus y the whole square. So the second moment of an area is nothing but moment of inertia. So this is the moment of inertia of the elemental area dA about the axis AB. So to find the moment of inertia of the entire lamina about the axis AB, we can integrate this term. Okay, so let us denote it as IAB. So what is IAB? IAB is the moment of inertia of the entire lamina about the axis AB. So IAB can be found out by integrating the moment of inertia of the elemental lamina about the AB axis. Okay. So now let us expand this term. That is equal to integral dA into h square plus 2hy plus y square. That is equal to, let us open the bracket. So this will become integral h square dA plus integral 2hy dA plus integral y square dA. That is equal to, now let us consider each term separately. So what is first term? Integral h square dA. So in that, h is a constant. So we can take it outside. So this can be written as h square into integral dA plus 2hy dA. Again 2h is a constant. We can take it outside. 2h into y dA plus, what is y square dA? So y is the perpendicular distance from the elemental area to the centroidal axis. So y square dA means it is the second moment of this elemental area about the centroidal axis, or it is the moment of inertia of this elemental area about the centroidal axis. So y square dA is the moment of inertia of the elemental area about the centroidal axis. So when we integrate that term, what we will get? We will get the moment of inertia of the entire lamina about the centroidal axis. So let it be denoted as Ig. So what is Ig? It is the moment of inertia of the entire lamina about the centroidal axis. So this is equal to, you can write Ig as the first term plus, we will consider this term h square into integral dA. So h square is a constant. What is integral dA? Nothing but a. So this term will be ah square plus, what is this term? 2h into integral y dA. So what is integral y dA? For that, let us see what is y dA. Y multiplied by dA. That means it is the first moment of this elemental area about the centroidal axis. So when we integrate this term, what we have to take? We have to take the first moment of this entire lamina about the centroidal axis. So 2h into integral y dA means we have to take the first moment of the entire lamina about its centroidal axis. So we have to multiply the entire area with the perpendicular distance from the centroid of the entire area to the centroidal axis, which is 0. I will explain it again. That is, dA into y means it is the first moment of elemental area dA about the centroidal axis. That is, we have multiplied dA with the perpendicular distance from the centroid of dA to the reference axis, that is the centroidal axis. So when we integrate this term, we will get the first moment of the entire lamina about the centroidal axis. So how will we take the first moment of entire lamina? For that, you have to multiply the area of the entire lamina with the perpendicular distance from the centroid of the area to the reference axis. So here the reference axis is the centroidal axis itself. So the perpendicular distance from the centroid of the area to the reference axis is 0 since centroid is lying on the axis. So that is why this term is 0. So this entire term vanishes. So this will be equal to Ig plus AH square. That is IAB is equal to Ig plus AH square, which is the parallel axis theorem. Let us state the parallel axis theorem by seeing the figure as well as the final expression. We can simply state the theorem. That is, if Ig is the moment of inertia of a plane lamina of area A about its centroidal axis in the plane of the lamina, then the moment of inertia of the area about any axis AB which is parallel to the centroidal axis and at a distance h from the centroidal axis is given by IAB is equal to Ig plus AH square. Hope you understood the video. Please share your comments and queries in the comment box. And please don't forget to subscribe and share the channel if you like the video. Thank you for watching.